You're conducting a test of independence for the claim that two different populations have the same proportions of the following two characteristics. Here's the sample data. So it says I've got population 1 and 2, and they're broken up into two separate categories. Whatever these categories are, they didn't give us anything, but we'll call them category A and B. So the important thing here is to remember that we're testing the claim of independence that these two populations have the same proportions for these two characteristics, and that's important. So what the question's ultimately asking us to do is to come up with the chi-square test statistic for this data. Well, in order to do the chi-square test statistic, we're going to have the sum of all of the observed values minus the expected values squared divided by the expected values. So we're going to have to calculate some of these expected values and talk about what that means. These are all of our observed values. So we're going to need to think about what this expected idea means. So there's a formula. The formula says you take the row total of this matrix, you multiply it by the column total, and then divide it by the table total, and that gives you the expected count for the expected matrix. But let's talk about why that's true. If we think about these proportions, these two populations are supposed to have the same proportion. And the level of difference, for example, that we see here between population 1 and population 2 is supposed to simply be due to random chance if the null hypothesis for this chi-square test is going to be true. So then we're going to have to think about, well, if these are different from each other just because of random chance, okay, well then we can treat this 96 out of this 236 as if it was the combined total of these two group A's. So what am I thinking? I'm thinking in group A, I've got 96 out of 236. That's my success rate for group A, regardless of which group these people were in, whether they were in population 1 or population 2. The overall success rate for group A was 96 out of 236, which is what as a proportion? So let's go 96 out of 236, and that is basically 41%. So roughly 41% of the group should be group A out of this population 1. Okay, well if that's my overall success rate, and that's basically 41%, then if the null hypothesis is true, that the level of difference is in fact just due to random chance, then I can treat this 41% success rate as the overall success rate, and then I can simply multiply it by this total of 56, because I had 56 people in group 1, and I expected 41% of them to be in group A. So I'm going to take that number, 0.406, and multiply it by this population total for population 1 of 56, and I get 22.77. So therefore, in my expected matrix, if in fact the truth is that I was expecting 96 out of 236 of this 56, then that should be an expected count of 22.77. Now notice what I did. I took my row total, 96, divided by the table total. So right there is my overall success rate. And then when I multiply it by the column total, I'm just saying, given this success rate is the assumed truth, then out of this 56, we would have expected 96 out of 236 of this 56 for this 22.77. So then I would just keep doing that. I would just take, okay, so now I'm going to take, for what proportion of group 2 did we expect to be in this group A? So again, it would be 96 out of 236 times this 180 now. So I'll do the same thing. I'll take 96 out of 236 and then multiply that by 180, and that gives me 73.22. So there's my expected count there. Okay, so then I would do it again, but now I'm going to move on to this category B here, and I've got a new overall rate, right? I've got 140 out of 236. So the combined proportion there of 140 out of 236 is 59.3%. And again, I could have just subtracted the 40.6 from 100% to get that 0.593. But again, there's my success rate, 140 out of 236. And then I'm going to multiply that 59% times 56, and I get 33.22. And you can tell if you've done that, right? Because notice what those two add up to be, right? So that's 22, 55, 56, adds up to 56. So those two should sum up to the column total. So, and we'll just do this one by shortcut, since I know that there were 73.22 out of this 180. So I'll go 180 minus the 73.22, and we get 106.78. So now I've got my expected matrix. So notice what the chi-square number is, right? It's the sum of all of our observed values minus the expected values squared divided by the expected. Well, I've got my expected values, I've got my observed values, so now I just need to do this formula 4 times. So what do I have? And I'm just going to show the first step to it, and then I'll show you how to do it in the calculator, because this gets really tedious. So the sum is equal to, so I'm going to take my observed, 31, minus what I expected, 22.77. We're going to square that, and then we're going to divide that by 22.77. Plus, then we're going to do it again, 65 minus 73.22 squared, running out of room there, divided by 73.22 plus 25 minus 33.22 squared divided by 33.22, and the last one's going to be 115 minus 106.78, and we're going to square that and divide it by the 106.78. So now you've got a lot of arithmetic to do here. So I'm just going to do this very first one so you can see what that comes out to look like. So I'm going to go 31 point, am I on the screen? Yep, 31 minus 22.77. And then we're going to square that, and we're going to divide that by 22.77. So what do I get? 2.97. So this first value is 2.97. And I'll just go ahead and do a couple more. So, so then I'll do the next one. So we'll do it all at once here. We'll go 65 minus 73.22 squared divided by 73.22. And that one is 0.9228. We'll do the next one. 25 minus 33.22. Square that and divide that by 33.22. And I get 2.034. And then the last one, 115 minus 106.78. We'll square that and divide that by 106.78. And we get 0.63. Yeah, and so then we'll add those up. So what do I have? I've got 2.97 plus 0.9228 plus 2.034 plus 0.633 is 6.598. So the sum is equal to 6.598. So now I'm going to show you a quick and easy way to do all of that work in the calculator. So in order to do that, we're just going to enter this matrix. So we're going to take the red pill, or is it the blue pill? I forget. So we go to matrix, go to edit, and it's 2 by 2, so 2 enter, and it's 31, 65, 25, 115. And so now I've got matrix A. So then I do not need to calculate this expected matrix. The calculator is going to do all that for me. So I'm going to go stat, test, and then I'm going to just scroll down until I find the chi-square test that I want. So remember, if you have an older calculator, it doesn't have this goodness of fit on there, but we're doing just the straight up chi-square test. That's our association and independence test. So we'll do that. Notice it says, hey, is your observed matrix in matrix A? Yes. Do you want your expected matrix in matrix B? Yes. Go down to calculate, hit enter. Notice 6.556, 6.598. I'm a little bit off due to rounding. but it's pretty darn close, right? So there was a ton of rounding that took place in there. 6.598, that's roughly 6.6. And if 6.556, that's roughly equivalent to 6.6. And then here's the associated p-value and the degrees of freedom.